Welcome back. So we have been looking at how to solve generating recurrence relations using generating functions. So to quickly recap recurrence relations, we have gone through this definition a few times already. It's a sequence of numbers where we have been given the initial set of numbers and the nth term is written as a function of the previous ones. Recurrence relations is extensively used in various subjects. We have seen how recurrence relations can be used for modeling problems, and we have been trying to see how to solve recurrence relations. Now there are quite a number of recurrence relations examples that we have looked at. The main question is, how do you solve them? So the technique that we looked at is how that if you can guess the solution, then we can prove it using induction. Once you can guess it, proving it using induction is quite a straightforward thing. The main issue being, how do we guess the solution? The first technique is, of course, you can guess it by unfolding the definitions. And we have seen how that can be used to guess it correctly. But then there were other things like the Fibonacci number, which we didn't know how to guess. And then there are other things like the recurrence relations coming from the binary search and so on, where again there was no nice guess. So in that case, in the second case, when there is no nice guess, we told that okay, maybe we can come up with a upper bound and lower bound, and that should be good enough for us, at least using the asymptotic rotations of big O, big omega, theta and so on. We can possibly get a asymptotic function for the recurrence. For example, we looked at this recurrence, and the idea is to first guess mn for some particular n, and then you use induction to prove that mn is theta of some function, which whatever you have guessed till now. That is done by proving an upper bound and lower bound. So this is what we were there using the simple techniques of doing recurrences or solving recurrence. There was also the master's theorem, that was a kind of nice theorem to deal with a quite number of different style of recurrences in one go. But still there are recurrences, for example this one, the Fibonacci number, for which we don't know how to solve it. Neither do we know how to get an approximate solution. And we have been telling it that it's hard to guess and hard to get an upper bound and lower bound, and the reason being that actually Fn is of this form. Now we are going closer and closer to actually proving to you that Fn is of this particular form. To start with, we looked at this new technique called generating functions. The main idea is that if you have a sequence of numbers a0, a1 till a infinity, you first represent this sequence of numbers as a polynomial, infinite polynomial, which we sometimes call power series, where the p of x is a0 plus a1x plus a2x squared plus it goes on, or in other words, summation of an x power n. Now once we have this polynomial, this is called the generating function for this sequence is a0, a1 and so on. The idea being, if we can somehow compute the nth coefficient of x power n in px, then I get a formula for an. Now in the last video, we saw how this technique can be applied to solve when the recurrence was of the form an equals to 3 times an minus 1. Now in this video we will see one more application of this generating function, and that will be again something that is not new. We will be solving the Tower of Hanoi using generating function, but we will see how one can apply generating function there. In the next video, we will be seeing how to apply generating functions to get the formula for Fibonacci numbers. So before we go on to generative functions, one of the crucial components of this technique is to use the generalized binomial theorem to get the Taylor expansion. Now once you have the Taylor expansions, you don't really need to prove it again and again. You can use these Taylor expansions if and when it required. Right? Here is some of the useful Taylor expansions that are there. Now let's look at the example of today, which is the Tower of Hanoi. This is our old friend. It says that h1 equals to 1 and hn equals to 2 times hn minus 1 plus 1. Remember that we did solve this particular generating recurrence relation in the first technique only, which is unfolding the definition. But today we are going to solve it in a different style using the generating functions. It would be useful for us to see how the generating functions can be used to solve this kind of stuff and help us to understand the generating function machineries better. Now for generating functions, we always start with defining the generating function, namely the polynomial. So here it is. So px equals to, now note that here I am defining it slightly differently. I am defining it as h1 plus h2x plus h3x squared and so on. So that means the coefficient of x power n is hn plus 1. Remember that, okay? That's most important. I am not defining h0 because h0 is not known, right? Now, again, what the idea is that I can write from h2 onwards, I can write it as h2 I can write 2 times h1 plus 1, h3 is 2 times h2 plus 1 and so on. So this one, note that here everything breaks down to 2 times h1x plus x, 2 times h2x square plus x square. So in other words, I can club them together to get h1 plus 2x, of course we take out, and then I get h1 plus h2x plus h3x square and so on, plus the remaining, like this ones, right? Which is x plus x square plus x cube plus so on. Now of course, like last time, this one is nothing but p of x, right? So I get, before I go on to do that, note that this number is what we had done in the Taylor series is 1 by 1 minus x, right? So what do I get? I get that, so sorry, not this one, this plus h1 is 1 by 1 minus x. So I get p of x equals to twice x times p of x plus 1 by 1 minus x. And this is the kind of place where we want to be, because this is, as we saw in last time also, this helps us to say that if I define p of x like this, I can get px equals to 2x times px plus 1 by 1 minus x, or in other words, px equals to 1 by 1 minus x into 1 minus 2x. Now this is a very useful way of doing it, because now again we have written down the polynomial as or this function px as a function which has nothing to do with recurrence. So all I need to do is now understand what are the coefficient of this formula or this function. And of course we have our Taylor series in handy. Right? So this is, let me pause here a little bit. The idea is we started with this polynomial and then we use the recurrence relation to write down the polynomial as to write an equation on the polynomials, and we got something like this: p of x equals to twice x p of x plus 1 by 1 minus x. and hence P of x equals to 1 by 1 minus x times 1 minus 2x. Now it's a very simple thing that I did, or this generative function is an extremely powerful tool, and this is how it basically goes always. You start with the generative function and then use the recurrence and whatever things that you know to get a function or write the polynomial P of x as a function of x. And once you do it, our goal is now reduced just to understanding the nth coefficient of this function that we have. Sometimes that might be easier said than done, as we will see now. But as we saw in the last time, that we had something like 1 by 1 minus 3x, and we could apply the Taylor series immediately. So this is where we are now. We have written P of x as 1 by 1 minus x times 1 minus 2x, and all we want to do is understand what the x power n, coefficient of x power n in this function. Now, in the Taylor series, in the generalized binomial theorem, or in the Taylor series expansion, I could write the Taylor series of 1 by 1 minus x, or I could also write the Taylor series of 1 by 1 minus 2x, but writing down the Taylor series of product of them is not easy, because there is no direct way of writing it. Okay. We don't know the Taylor series of this. So we do a small trick. Let's see, what do we do? We started with this P of x and we wanted to do this one. The trick that we do is, I write P of x, so this is P of x, I write this expression 1 by 1 minus x and 1 minus 2x as 2 by 1 minus 2x minus 1 by 1 minus x. Just check out that this is actually true. So, in other words, this is a 1 by a polynomial of degree 2. I have written it as sum of 2 inverses of polynomial of degree 1. You can check that this equation is right. And once we see that this equation is right, this one, I know how to use what is the nth coefficient of this one using the Taylor series expansion. I also know the nth coefficient of the x power n in this function, again using the Taylor series expansion, and hence in the subtraction I will be able to understand the coefficient of x power n by subtracting the coefficient here minus the coefficient here, right? And this is what we will have. For example, Px here will become 2 times, now I just apply the Taylor series here, which is 1 minus 2x, the Taylor series of that is 1 plus 2x plus 2 square x plus 2 cube x cube and so on, and 1 minus x is 1 plus x minus x square and so on. So P of x is this expression, and hence you can already see that the coefficient of x power n is 2 times 2 power n minus 1, right? And this is what we wanted. So we had this one, and we have got P of x as this expression. So the coefficient of x power n is 2 times 2 power n minus 1. Now, since the coefficient of x power n is hn and not hn, coefficient of xn minus 1 is hn. So, to understand what the function of hn is 2 times, so is the coefficient of x power n minus 1, which is 2 times 2 power n minus 1, which is 2 power n minus 1. And we know that this is right because we have done it earlier also. The idea is not whether the generative function can solve this one or not, but this is a generic approach to solving recurrence relations. It's a very powerful approach, and we will see in the next video how this approach can be used to solve the Fibonacci number sequence. That will be possibly the high point of this course, where we solve the Fibonacci numbers using generating functions. So we have seen how one can use generating functions to solve tower of Hanoi. We have seen that we first represent it as a polynomial, then use the px and write px as a function of x. And once you have a function of x, you use some amount of tricks to and some Taylor series expansion to write the Taylor series expansion of the whole thing, which helps us to understand the coefficient of x power n and hence get a compact form for the recurrence relation. In the next video, we will be doing the Fibonacci numbers. Thank you.